Good morning. Let us start the second lecture of this week. We were discussing the important spectroscopic technique called circular dichroism, and in the previous lecture we looked at that any unpolarized light, by some manipulation we can make it polarized, we can make it linearly polarized light, we can make it circularly polarized light, we can make it elliptically polarized light, right, by just playing with the like a electric vector and magnetic vector, how they oscillates when they propagate. Now, for polarization we also looked at what kind of tricks or techniques that can be adopted, and one can have a linearly polarized light as well as circularly polarized light. That is what we discussed. Now, where we are going to use, right, why we have to do it. So, linearly polarized light, what kind of application it has in a science. CD I talked to you about protein secondary structure determination, but even linearly polarized light has an important function to play in the science, right. So, what optical activity measurement we do by an instrument called polarimeter, and that basically measures the chiral molecules rotate under this linearly polarized light. So, rotation, chiral molecule rotates linearly polarized light. So, our light was coming a linear, right, and here is a chiral molecule. It rotates by an angle theta, and then that rotation depends upon the specific rotation of that molecule alpha equal to concentration of this molecule and the path length through which this light has gone. So, if you take a linearly polarized light and shine that light onto some chiral molecule, light gets rotated and then you detect that light. So, if you detect that, you can get the idea about this chiral molecule. So, say for an example, sucrose, sugar, glucose, lactic acid, fructose, all of that has some alpha, that is at 20 degree. So, sucrose has this specific rotation 66.4 degree per gram ml per dm, and it is that can be used for sugar content analysis, right. You remember where you can do the sugar content analysis, right. Even glucose sugar content analysis. So, you are drinking, say, I do not know, right, a cold drink or soft drink and all those, and it is written that not less more than 20% or 10% sugar is there. How you determine it? So, this is the optical rotation as an important tool which can be thought of using this for sugar content analysis. Another, glucose, important component that needs to be detected. So, it has this 52.7 degree, that specific rotation alpha and beta, and it is used in diabetic diagnosis. So, blood is taken and you can measure how much load of glucose is there in the blood. Even in the fermentation technology, right, it is a continuous manufacturing nowadays people are talking about. You need to keep monitoring how much you are feeding into the media and how much is coming into spent media. You can find it out because glucose is a source where our microbes grow, and therefore, determination of those are very important and you can use that. Third one is lactic acid, it is a food quality or even bacterial metabolism. If there is not enough oxygen, they do not degrade glucose into something, and lactic acid formation happens. So, in those case it has a alpha of 2.6, you can put this lactic acid, shine the light, and you can find how much rotation is happening, and or then you can determine the what is the concentration, right. So, it is like a simple UV visible kind of relation you have. Fructose, honey composition analysis. Now, it again has a alpha at 92.4, and one can use this for honey composition. Honey is nowadays getting adulterated, and it is one of the very important food ingredient. Also, it has lots of medicinal property. So, people pay to buy a good quality honey which has a medicinal property, not only sugar syrup, right. So, in those cases, doing the composition analysis and assuring that honey whatever is being sold in the market is correct or not. There are some spectroscopic technique. One can is as simple as this linearly polarized light based polarimeter. One can measure the component. You can have a clinical use of this by measuring the blood glucose by optical rotation. So, in the food, in the industry, in the beverage, even in the clinics, you have the use of linearly polarized light. And circularly polarized light, we already discussed, it is about protein structure. Now, why protein structure? Because you know there are two components of circularly polarized light. One is left handed circularly polarized light, another is right handed circularly polarized light. And in this case, it is not like a rotation, but absorption of these, the left handed versus right handed, happens differently by this chiral molecule. So, that delta A, the absorption of left handed polarized light minus right handed polarized light, that gives you the differential absorption and that gives you CD signal. So, we can measure the CD signal 2.303 multiplied with a difference of left handed and right handed, that is called ellipticity. So, you see where ellipticity term is coming. If the two vectors, so like circularly polarized light, x and y vectors are same, but if differential absorption happens, so one like a say x vector and y vector are not absorbed same, then this vector will reduce little bit, but this vector reduces quite a bit. So, rather than its being circular, it becomes elliptical, So, this x vector is absorbed more. Now, what it comes out is elliptically polarized light, and that is what you measure something in CD called ellipticity. So, that is measured in millidegree or absorption unit. Now, this ellipticity is extremely important signature for protein structure determination. So, if it is alpha helix, I am just giving you a brief alpha helix, the lambda minimum is like a when you measure this ellipticity versus ellipticity theta versus lambda, you get two minima for alpha helix and one maxima for alpha helix, right. So, minima is 222 and 208, lambda max is 190 to 195, 2 negative band, and that is what you have at minus 20 millidegree typically at minus 222. But when this different kind of secondary structure, that is beta sheet, this lambda shift and it goes around 215 to 280. Now, like lambda max here, so for say helix it gives something like this, right, and for beta sheet it can be something like this. So, looking at these peaks, you know whether protein is helix or sheet. For beta sheets 215 to 220, positive comes at 195, one negative weaker peak you have, and typically absorption happens minus 5 to minus 10 degree. Random coil, no minima, so lambda max 200, it is a weak positive near 0, and mixed you can have multiple band variable combined pattern you get, and now if your protein is mixed, you need to really deconvolute each of these component, and that is again a very important one. So, that is what we are going to talk about, little bit of theory, implementation, theory and application of circular dichroism in protein structure determination. So, let us start with little bit of theory again too. After giving you this brief glimpse what we are going to venture into, we will be talking about instrumentation, theory and application of CD. Now, CD, it is an spectroscopic technique that measures the differential absorption of light. What kind of light? Left handed circularly polarized light and right handed circularly polarized light. So, it measures actually delta A of left handed polarized light minus right handed polarized light by a chiral molecule, and this absorption, the difference in absorption provides a rapid structural analysis of biomolecule in solution. The instrumentation, what kind of instrumentation you require? So, you require a light source, of course, you require a monochromator and photoelastic modulator, then we require a sample cuvette, right, and then some PMT detector which gives you high signal to noise, right. So, first we require a light source and then something which can convert this linearly polarized light or unpolarized light to circularly polarized light. And then you requires a sample, then detector, right. So, that is what we can have it. Now, the spectral region where we are going to have, so since the protein basically, if you remember in UV visible we have said that it can absorb between say 170, 180 to 250 for the secondary structure. So, one can probe this far UV region of 165 to 250, where transition happening essentially from this peptide bond, right. And that peptide bond, it differentially folds to form a secondary structure. Now, peptide bonds folding into different secondary structure, it is a helix or sheet or random coil, gives you idea how the what kind of structural elements are there. You can use CD also in the near UV range between 250 to 320, and that measures basically this absorption happens because of presence of 3 aromatic amino acid that we have, tryptophan, tyrosine and phenylalanine. So, by measuring the presence of these, whether they are buried, exposed, what is the local environment, you can get idea about tertiary structure of this protein and local environment. So, now we can measure confidently and clearly the secondary structure elements present in the protein, and therefore, we can apply this technique for protein folding study. We can apply whether protein is stable or not. So, we can change the temperature and look at the protein that is opening and closing, protein folding or unfolding. One can have melting or stability of a protein. One can measure the concentration of DNA, RNA, nucleic acid, what kind of structure it has, B form of DNA, A form of DNA, G form of DNA, quadruplexes, all of these we can have. We can have a therapeutics protein, right, one can measure, protein can be measured. So, therapeutics protein quality control we can have, like a monoclonal antibody, vaccines, biologics, biosimilar, their ligand binding study, all of these can be used for biopharmaceutical application by measuring this. Then we can have a deconvolutional algorithm, because you know protein is never pure, it gives you mixture, right, as we talked about here, it gives a mixture of a structure. So, you need to have some deconvolution happening, and the manufacturers have come up with, or even scientists have come up with different deconvolutional algorithm. One of them is Bestel, the dichrome wave or K2D3. These are the software that basically helps you in analyzing the content of alpha helix, beta sheet, random coil, right. So, they basically it has a database coming from about 500 proteins or something, and it is kind of a, I would say now we are in AI era, but this is a kind of AI which has learned about the protein structure, and now you give a new protein, basically it tells you by looking at the spectra and calculating the percentage of helix, sheet and random coil, and with very high accuracy. Root mean square deviation or error, root mean square error is less than 0.01. So, advantage is that it is a fast, it is a solution based, under physiological condition you can get the structure of or structural elements of protein. You require a very low concentration of protein, typically in microgram. You can do in a real time kinetics whether the binding of a protein changing the structure. So, you can have a real time, it is a cost effective, it is not like a about say $10 to $50 per sample. So, like a 2000 to 5000 rupees per sample. You requires minimum salt and buffer interference can be there, because we can subtract that, and it makes an ideal technique for biomolecular characterization. Also for industrial application, it gives you idea about quality control, right. So, important technique, just to recap you, we are measuring the differential absorption of light handed polarized circularly polarized light and left handed circularly polarized light by a chiral molecule, and our biomolecules, most of them we talked about are chiral. So, essentially key definition is we are measuring the delta A difference in the absorption, which will be absorption of left handed minus absorption of right handed, right. So, you can just bring your basic concepts from the first week lecture, it should be EL, that extinction molar absorptivity or extinction coefficient of left handed polarized light and right handed polarized light, and concentration and path length, right. So, EL are molar absorptivity, the liter per mole per cm, C is concentration, L is path length. Now, that is the definition of this. So, this is linearly polarized light, this is circularly polarized light, how these two different circularly polarized light absorbs, that is measured in this sheet. Now, there is effect, this is popularly known as cotton effect. So, when the circularly polarized light interacts with a chiral chromophore, we have a birefringence, like a velocity difference of left handed and right handed polarized light. That circular dichroism absorption difference happens, right. So, linearly polarized light becomes elliptically polarized light, I talked to you about, because they are absorbing differently. So, rather than it is becoming circular, one axis becomes longer, like a more than other axis, now it is elliptically polarized light. So, after absorbs it. So, handedness you can find it out left by right makes the molecular chirality, and this was discovered by Jean Baptiste White. Modern instrumentation start to coming in 1960 and 1970, and now we have wide spread application of protein structure that started after 1980. So, you see it took more than 100 years, 150 years from the discovery to the application. So, that is how science moves. First you discover the concept, then engineering solution comes, they make the instrument more sensitive, because protein concentration are very low. So, after all the instrumentation that happens over the year, we can have the instrument and we can measure it. So, what we are going to have is, in instrument we are going to have a Zener arc lamp, which can give you radiation in the range of 165 or 163 to 950 nanometer. Then we have a monochromator. So, this is our Zener arc lamp. Then we have a monochromator here, grating, and grating basically is like we can have a bandwidth, variable bandwidth, that diffracts grating. Diffraction was one of the way to make it polarized. So, here we have a linearly polarized light that is coming, and now linearly polarized light 45% of incidence and 45% transmission. So, grating resolution one can have is 1000 to 2000 line per mm, and one can control the bandwidth. So, essentially that is the light source we are talking about. We are starting with a Zener lamp. By putting the gradient we generate the linearly polarized light, right. So, that is a, you require a decent power, right. Power output should be about 500 watt, and then some warm up, and then operating voltage should be about 5 to 6 kilovolt. Grating already specification we discussed. Then you require a linear polarizer. So, here you require a linear polarizer. So, this can be calcite based prism, or that converts the light into linearly polarized. So, here we are going to have, after this linearly polarized light, 50% goes as linearly polarized light, 50% transmits, right. And then after that you can have a sample cuvette, right. So, sample cuvette can be far UV or quartz cuvette that can have a path length of ranging from 1 mm or 0.1 mm to 1 mm and 10 mm depending upon what we want. And then like we have a temperature control, because we want to do the differential temperature experiment, and one can have typically sample which is sitting in this quartz cuvette. So, that is a 200 microliter. Now, that is the important. So, we have a linearly polarized light, right. So, after linearly polarized light, what we have to do? You have to make it circular, like make a linearly polarized light can be decomposed into circularly polarized light. So, linearly polarized light 50% incidence. On the quartz we can have alternating left and right handed polarized light at 50 kilohertz per mm. So, phase modulated output we are going to have, and that can be done by this piezoelectric driven quartz resonator that oscillates at 50 kilohertz, resonator which oscillates at 50 kilohertz. Now, we induce and birefringence is happening because of the, basically it is a property of two solvent, refractive index difference, and you can have birefringence because of that. So, it creates the quarter wave, and that one is retarded alternatively, and it converts that linearly polarized light into right handed and left handed polarized light. So, now that can modulate it, and you can have advantage that no mechanical moving part you need, and you can switch the rapidly, and now we have these two different polarized light coming out from this, right. So, after that, now we have the light source, we generated it, and we can put it left handed polarized light, right handed polarized light, it is coming out from here. So, one can have basically these two lights we have, then we can have the sample, and after sample detector. So, after that what we have detection and signal processing, one can have a photomultiplier tube, which basically is measuring how much light is coming after passing to the sample. So, it should have highly sensitive, because signal can be very low. So, gain should be 10 to the power 6 to 10 to the power 7, response time should be very good. The wavelength range that it absorbs is 190 to 900 nanometer, and it should be like some specifications like dark current and all those, right. Then you can have a lock-in amplifier, then important part, because we are working in a UV regime. So, constantly this has to purge with a nitrogen, because oxygen is present, right. So, oxygen can also absorb in the range of 200 nanometer. So, we do not want oxygen to be there. So, we purge with a nitrogen, right. It can eliminate the ozone formation can happen. If the UV light falls on oxygen, it becomes ozone, and that can interfere with our signal. So, constantly we purge with nitrogen, right, purge with the nitrogen to make it inert environment, and that should be constantly purged. Then we have electronic and software, because we are detecting those data on electronic, and one can calculate that theta that we are talking about, the difference in left handed and right handed polarized light, and we can have a temperature setting, because we can change the temperature for detecting it, right. So, essentially we are moving with these two components, that we are detecting the differential because of differential absorption because of chiral molecule, we are measuring the change in the electric and magnetic component. So, E and B rotates clockwise, E and B rotates counterclockwise, and you measure this difference for the chiral molecule. So, you can have a enhanced interaction if lower alpha happens, and you can have out of phase or other reduced interaction if higher alpha is there. So, that differential absorption we are measuring, and that is giving delta alpha, that as a CD signal. Now, important parameter what we detect it and how we interpret or represent those data. So, basic concept, we have the light from which is coming from the instrument, left handed, right handed, we have a molecule in solution which is chiral. This chiral molecule absorbing differentially delta E, absorption of the left handed, absorption of the right handed, that we can measure delta E equal to C and L. This is an unit which is dimensionless, because absorption does not have a dimension. So, we can have a dimensionless differential absorption, but we measure the CD in ellipticity, because you see that tan angle that we have, tan theta basically in millidegree, that is differential absorption that we talked about. So, differential absorption, if you remember how much it is in the last lecture we have said how much they rotates and gets polarized. I will be discussing this as we go more. So, that theta, the rotation in the angle that we measure, and this is in millidegree, it ranges between minus 200 to plus 200 millidegree. Now, this is ellipticity. If you factor that concentration into that, so that will be called molar ellipticity, that theta divided by 10 C and L, that will be degree, centimeter square, decimeter square, that will be molar ellipticity. We can convert that theta equal to 33,000 into delta E, which is coming from here, that will be molar ellipticity, and then one can also measure this mean residue ellipticity for proteins. So, how many residues are there? You can divide that here. So, NR is number of residue that will give you mean residue. So, you can either measure ellipticity, molar ellipticity or mean residual ellipticity, helps in normalizing to the residue and easier for comparison across the protein of different shape and size, because a bigger protein can have a different molar ellipticity or ellipticity, and if you factor in this will be concentration dependent, if you factor this it will be per residue contribution. So, these are the different way we represent the ellipticity, right. Now, as I said, these are some of the algorithm that helps you in determining. So, what we get is this theta, and these basically dichrome or Bechtel are algorithm that learns from the machine, from the database, and typically it fits the mathematical equation, the component of helix, sheet, noise, all of these, fraction of secondary structure, helix type, beta sheet, random coil type, and matches with some reference spectra to give you output in terms of percentage helix, percentage sheet, percentage random coil, and some root mean square error, right. So, typical results we get alpha helix, that you put it 33,000 per degree, because that is a theta for this, beta sheet and random coil. So, these are the results we get it. We can also use this for like a thermal melting analysis. So, what is the fraction unfolding? If we take a protein at 25 degree, we believe that it is folded, and if we keep increasing the temperature, your CD signal changes, and that you can measure it. Fractional unfolding, so you can have a theta of any temperature T, theta of folded unit, theta of unfolded unit, theta of again folded unit. So, with this relation, how much at any temperature T, the fraction of protein is folded, that is what one can calculate it. So, that transition midpoint you can find it out 50% folded and unfolded, and you can create this Van 't Hoff analysis to find the thermodynamic parameters such as delta H, delta S, delta G, and you can have the very nice protein folding algorithm. Only assumption that we are saying only folded and unfolded, there is no intermediate. So, for two state protein folding, one can beautifully determine the fractional unfolding at any temperature by protein. Where are you going to use? Say we produce the protein at 4 degree, right, we all the time do in cold room or at ice, but application of protein is at different temperature. So, this simple analysis helps you at 45 degree for industrial application, my protein is folded or not. So, such analysis you can do by just measuring the protein stability or fractional folding using circular dichroism, right. So, that is what we are talking about, that is the differential absorption of left handed by right handed. You measure the ellipticity, right, ellipticity, and that is a delta A. You can have the difference in the right handed and left handed. You can calculate and find it out secondary structure of any protein by measuring this differential absorption of left handed and right handed, right. So, you have the ellipticity, the difference in the absorption, one can have a calculation of theta, you can have a calculation like a theta is 16.5 millidegree, say concentration of protein is this much, path length is this much, this is the ellipticity, you can find how much ellipticity is coming out. So, this is the degree per minute. You can calculate the mean residue and the molar ellipticity by normalizing the concentration and mean residue. So, you can have depending on protein size and all those. So, we will continue this discussion in the coming class. Let us end it here for today, and after when we come to the next class, we do this calculation how we can deconvolute and find it out the exact protein concentration by using circular dichroism and this concept that we discussed today. So, thank you very much. I look forward to having you in the next class. Thank you.